Hi everyone, thanks for tuning in. This is Andrea from Greenden. In our last video, we showed how to set up a simple neural net with the bodyfat.csv dataset, which we downloaded from Kaggle. The link is in the description box below. In this video, we will show how we can improve neural network performance by adding inputs and by testing different activation functions. In our last video, titled Simple Neural Net with NNetDesigner, we set up a neural net with 4 inputs to learn density and % body fat. To recap, here we show the simple 4-input neural net and its training graph. After about 6 million epochs and 3 hours and 15 minutes, the RMS error was about 0.034. Let's take a look at the data. As we can see, the neural net output for some data points matches the dataset well and less so with others. Let's work on improving the design. We will unpin the graph and pin the Properties dialog box. We also click on Clear Graph to clear the previous output data. If we look at the bodyfat.csv data, we can see that, as before, we have 2 data fields that we can use as outputs and 13 fields that we can use as inputs. We need 13 inputs, so we'll copy and paste our existing inputs. We click Fit All and zoom out a little so we can fit the hidden nodes we're going to add. Then we copy and paste the hidden nodes that we need. Now we auto-route our connections. We select the nodes we want to auto-route, click Auto Connect, orient the big arrow, and click the mouse. To enable the selection of any object, we click All. Next, we manually connect the input nodes to the pre-processed nodes. We can't really use the auto-router here because it will fully connect each input to all pre-processed nodes, and what we need is a one-to-one connection. We connect our input nodes to the data by selecting the node and then selecting the data field in the Properties box. We select age, weight, height, and so on. Next, we're going to bring out the Process dialog box and normalize all the inputs. The outputs are still normalized because we copied them from the simple neural net and its outputs were already set up. Now we're going to look at the hidden nodes and verify that their activation functions are all sigmoid. We renamed the file to BMI sigmoid. Let's unpin the Properties view and then resize the window. As we resize the window, we can see that we have 4 instances of NetDesigner ready. We will go ahead and pick the next instance of NetDesigner and open the BMI Segmoid file. We click the Node selection box and select the hidden nodes. Under Properties, we select RelView. Notice how the hidden node's color has changed. Next, we will save the file, renaming it BMI RelView. We unpin the Properties view and reduce the window size. Now, we maximize the next instance of NetDesigner and open the BMI Segmoid net file. Repeating the same steps as before, but in this case we set the hidden nodes to the 10H activation function. Again, we save the file, this time naming it BMI 10H. Last, we maximize the remaining instance of NetDesigner and open the BMI Segmoid net file. This time, we'll leave the first 8 nodes as Segmoid. The next 8 nodes we'll set as RelView. The next 8 we'll set as 10H. And the last 6 we'll set as Shockley. We will then save the file, renaming it BMI Multi. We now bring out and pin the train graphs for all 4 windows. We click the Train tab, click the gears, and then randomize inputs, repeating for all 4 nets. Let's rescale the y-axis for all 4 nets so we can better see the training error. The first thing we can see is that the Segmoid net has a pronounced break here. The RelView and 10H, not so much. The multi-net has a little bit of a break. We let the nets run for a while. Okay, after training for a while, we can see that the Segmoid net has reached an RMS error of 0.0034 after about 3.5 million epochs. The RelView net has reached an RMS error of 0.0028 after about 1.4 million epochs. The 10H net has actually done the best, with an RMS error of 0.001 after 1.03 million epochs. And lastly, the multi-net has reached an error of 0.0029 after about 1.6 million epochs. We can now look at the data and see how the nets learn. For instance, the Segmoid net output view is shown here. Each output's training data is shown under the density and % body fat titles. The net outputs are shown in parentheses. Likewise, we can look at the RelView net output data. And the 10H net output data. And last, the multi-net output data. We we can click on Save at the bottom of each table and export the data to a CSV file so we can view it in Excel. While comparing a few points is helpful, we can also graph the data. This allows us to visually evaluate training accuracy for the full dataset. The graph we see now compares the improved 13-input 10-inch net with the simple 4-input sigmoid net. The train data is shown on the x-axis and the net output data on the y-axis. A perfect match would give us a straight line. We can see that the 13-input 10-inch net is quite a bit better than the simple net. Next, we compare performance for the 4 different activation function configurations for the 13-input net. We can see that all 4 nets perform pretty well. Looking at the inset, we can see that, based on how they fit an ideal line, the 10-inch net performs the best, followed closely by the multifunction net, then by sigmoid, and last by ReLU. For our next video, we'll look at classification using neural nets. Thanks for watching. We'll see you next time.